Okay, so it's nice to see so many people here. I'm Jonas Adomaitis, and today I'm going to present quantum machine learning with Qiskit. So the first question is, who am I? So I'm a data scientist and people manager at IBM, and I'm also a Gemini lover. So if during presentation you'll see a nice image with a gray star at the bottom right corner, well, you know that my friend has helped me with it. I'm standing in front of you not as a data scientist, but more like a quantum enthusiast. And I enjoy writing not only quantum waves, but the ocean ones as well. And also, I'm a Qiskit advocate. So, what the hell is Qiskit? So, Qiskit is the largest open source SDK for quantum computing. And for Pythonistas and data scientists, it will feel very familiar. It's like using scikit-learn or NumPy libraries. And if you want to build quantum neural networks or use one of the Qiskit functions, Qiskit will do the most hard work for you. So basically from optimization of your quantum circuits for the actual hardware, error mitigation, error suspension, and so on. So it is actually a tool what makes it work from quantum theory to your actual executable code. So you might ask, how do you start a quantum machine learning on a quantum computer you can see on the left? So as data scientists, we know that we need to spend a lot of time on feature engineering or data preparation. And with quantum machine learning, we have a new challenge, which is data encoding. And if I had one picture to represent this problem, it will look something like this. We say, oh, we have a nice Excel file. And quantum computer like, no, I'm not going to work with that. That's because quantum computers, we do not accept CSVs, Excels directly. We need to provide quantum states to them. And quantum state, you can imagine it as just being a huge vector in a Hilbert space. So you can imagine that data encoding is like building a bridge between a classical world and the quantum one. And this step is very important because if your bridge is not working properly, your model will collapse, no matter how many qubits you will use. And today I'll present 3 encoding methods that will help you to build a nice timing bridge. The first method is actually the simplest one, and it's called basis encoding. So imagine that we have a binary string of 1 or 1. Then what we can do is to encode those strings into qubit and into a quantum state 1 on 1. That's basically all it is. So this is good for cases where you have simple logic or some simple arithmetic. So if you want to implement a classical algorithm into quantum one, this is a method you want to go with. However, we have a lot of drawbacks with it. If you want to encode n-bit long string, you'll need n qubits. And currently for IBM, we have only in a matter of hundreds. So we can't really do anything practical with it. And this method, it doesn't take advantage of the vast quantum state spaces that quantum computers provide. So what we need is something a bit more usable, realistic. And the second method is called amplitude encoding. And this is actually where all the quantum magic happens. So in place of encoding 1 bit into 1 qubit, what we can do is use probability amplitudes of a quantum state to store our data. So imagine you have a bit string of a vector of 1024 features. So in practical terms, I would say it's quite a large vector. And if you use a quantum computer with only 10 qubits, what we can do is to create 1024 quantum states. What that means is that we can encode the full vector in probability amplitudes of just 10 qubits. And also, this is algorithmic scaling. So what that means? You can encode 1 million features, dimensions, into just 20 qubits. That's all you need. And this is an ultimate form of compression. So you can imagine that zip files in the future will be quite light ones. Although with this method, we also have quite a few drawbacks. So the first one is that your data should be normalized. So in a way that the squared sum of them, of your features, should be equal to 1. And another issue is that with current hardware, it is quite difficult to achieve that because it requires deep quantum circuits, and with current hardware will introduce a lot of noise. So basically you'll have probability amplitudes, but they will be started one, so not represent actual value. And if you want to do something practical, something useful, then you'll use angle encoding. And this method, instead of encoding something into bits or probability amplitudes, we use our features as rotation angles for quantum gates. So if your data is normalized between 0 and pi, what you can do is to apply rotation gate Rx to your qubit, and this way you'll just do the encoding. And this method is very hardware efficient. It keeps your circuits very short, very small, and yeah, it helps to avoid all the noise that probability amplitudes may introduce. So how do you select which method to use? If you want to do some simple experiments, some basic arithmetic, use Bayes encoding. If you want to explore the full Hilbert space, then use probability amplitudes, although you need to make sure that your hardware could handle that, because otherwise it will not work. And if you want to create something practical, then use angle encoding, so you can develop some useful applications. Okay, so now we know how to transform our data from classical to quantum one, but what interesting can we do with it? So most of you, at least I hope so, know about kernels. So just a quick reminder, if our data is not linearly separable, if you have blue circle in the middle, red circle outside of it, we can use kernel trick just to map our data into a high dimension, and I hope that our classes will be separable by a hyperplane. So this is how traditional kernels work, and what we can do is to introduce quantum kernels. So you might ask, what exactly is a quantum kernel? So it is simply a measure of similarity in a Hilbert space, and mathematically it's just an inner product between two states. And how the full pipeline works is that without any calculation of exact data points in our Hilbert space, we can run just a simple quantum circuit that computes similarity between two quantum states and provides us just one simple number, which is kernel entry. And in the quantum world, we call it fidelity. So basically, fidelity is a similarity measure that tells whether two states are different or not. If they are exactly the same, fidelity will be 1. If they are completely different, then fidelity will be 0. Okay, so if you do it iteratively across all data points, we will create a kernel matrix. And after that, we use that kernel matrix and put it to a classical computer on our laptops, for example, where you can run some classical machine learning, support vector machines or others. So as you can see, it is also hybrid workflow. It's quantum plus classical, not only quantum computer on everything. So a good question would be, why do we need quantum kernels at all? I mean, we have classical ones and they work pretty decently. So the answer lies in complexity. So some feature maps, some warpings of the data, are extremely easy for quantum computers to achieve. But for classical ones, it's just too difficult to simulate. So with quantum computers, we might create such kernel matrices that account similarities and correlations that are simply not visible to the classical ones. Okay, so this is how we can use quantum computers, but we didn't see any learning yet, didn't we? So can we do learning on quantum computers? And the answer is, of course, yes. I mean, otherwise I wouldn't be standing here. So we have relation quantum classifiers, and you can imagine them as equivalent of classical neural networks. So in classical neural networks, what we have are weights and biases. And in variational and quantum classifiers, VQCs, we have gates. And the logic is quite simple. So I don't know if you remember this game, but what you need to do is to connect correctly so the water flows. And this is basically how VQCs work. At first, we start with random gates, like this. And after that, we'll do forward propagation, forward pass, back propagation, and tell, okay, maybe I need to rotate that blue pipe by 3 degrees. And by doing so iteratively, we'll train VQC. So it is as simple as that. So now let's take a look at a full workflow and how it looks like. So as you can see, it's also a hybrid workflow. So it's not only quantum, but again, quantum plus classical. So quantum, a forward pass, how it starts, it's with data encoding. So it's the stuff that we have discussed just now. So first of all, we need to encode classical data into the quantum one. When this step is done, we have variational circuit. In quantum, we call it ansatz. So this is where actual learning happens. So we have our sortation gates, and when doing forward pass, we do some calculations, but after that we need to do a measurement. So in ansatz, we have quantum states, but in measurement we collapsing everything and have binary output, zeros and ones. And we provide this output to a classical computer, where it does a well-known classical stuff like calculating loss functions, using optimization algorithms to suggest how we can improve it. And this equivalent would be to the back propagation of neural networks. So classical computer, you can imagine it as being a manager. Basically, you're providing classical computer some work what you did, and manager says, okay, I think you should do this to improve your ansatz. And yeah, this is also done iteratively, and this is how VQCs are trained. I would say it's quite simple, but of course it will be a new information for you, and it's quite a lot. So we have talked about 3 parts: data encoding, quantum kernels, and VQCs. So this is just a theory, but can we use it in practice? So answer is of course yes, and we'll do it tomorrow. So my colleagues from IBM, Artem and Manta, will show you how to do quantum computing with Qiskit. We will show how Python code looks like. And yeah, come tomorrow at 2 p.m. Sorry, Artem, I'm not sure which room, but you can check it on agenda. And yeah, this is the way how you can start your quantum journey. So don't be afraid, don't be scared. As I mentioned, using Qiskit, it's like using scikit-learn. It's like import and doing some amazing stuff. Okay, and I have mentioned quantum circuits several times already, but what are these things at all? So they look something like this. We have a lot of different gates, and you can imagine them being as NOT gates, etc., etc. So yeah, you probably don't want to do it by yourself. It's like writing in assembly. So Qiskit actually has some abstractions already. and we call them Qiskit functions. So we're quite similar to Python functions in general, and we have two types of them. The first type is called application functions, and these functions are made for domain experts. So if you're an expert in chemistry or finance, you don't require any quantum knowledge. You can just supply classical data and you'll get classical output back. It is extremely simple. And the second type of Qiskit functions is circuit functions. So if you want to do some research or be just a cool quantum developer and build your own quantum circuits, you can use those functions. And why those functions are helpful? Because they help you to mitigate errors. They also help you to optimize your circuits to quantum hardware. And this step is very important because you can write a circuit like this, but efficiency, accuracy might vary on different hardware. So it's very hardware dependent. Okay, so let me share some examples of those Qiskit functions. I have introduced 3 of them, but you can check IBM's quantum platform where you'll see way more of them. So the first one is Quantum Portfolio Optimizer, and this function handles dynamic investment strategies without any quantum knowledge required from you. So basically what you provide to this function is some data like stock prices or investment constraints. And the function itself, it will do the optimization on quantum computer, and after that show you the best investment trajectories. So yeah, it's as simple as that. But behind that, we're using variational quantum eigensolver, and after that, we're doing some post-processing. So everything is under the hood. You don't need to worry about that. And the second is for ones who are interested in chemistry. So in molecular quantum chemistry, our main goal is to solve Schrodinger's equation. So basically, we need to find a ground state, which is the lowest energy state of a molecule. Sounds super fancy, and this is actually important because we need to understand how materials behave. And with simulations, we can do that. And the issue that classical computers have is increasing complexity. So it increases exponentially as molecules grow larger. And this function helps you to mitigate that. This is also a hybrid workflow, so it's not like quantum computer does everything. But first of all, quantum computer, it suggests you some electron configurations, and after that passes it to classical computer saying, okay, now we can finish up with quantum wave optimization and get a solution. And for the scientists, data scientists in the room, we also have a third function called singularity machine learning. So this function is also a hybrid model. It is quantum plus classical. So first we start with classical ensemble methods like bagging, boosting, etc. And after that we pass this ensemble model to a quantum computer to increase complexity and generalization as well. And this function is an exceptional one because it can handle actually a huge amount of data. Because the number of qubits, they tell you only how large ensemble could be. It doesn't matter how much data you have. So this is why it's super popular in different areas like finance, healthcare, and so on. Okay, so these are Qiskit functions, but how can we use, and has it been used in practice? So we have several options. So HSBC, Moderna, ICANN. So let's start with HSBC in the financial industry. So in finance, this is a difficult challenge to predict whether transaction will be filled or completed. And this is why HSBC together with IBM worked together to analyze a huge amount of data. We used more than 1 million real-world trades from a corporate bond European market. And they used a thing called quantum features. So basically, you can imagine it as being data encodings that we have discussed before. And the results that we have achieved is that we saw improvement of 34% relative ones in predicting whether customer's transaction will be completed or not. So in quantum world, it's quite a huge improvement. Next is Moderna. And as we already know, molecular structures are very complex to simulate. And Moderna, together with IBM, they used 80-qubit IBM's processor. And what they did, they successfully simulated folding patterns of mRNA. And it was 60 nucleotides long. So this one, I think, was last year, but it's still the standing record of simulating this mRNA sequence. So this is the longest one. And why does it matter at all? Because understanding these structures is the key to creating vaccines and therapies more quickly. And this also shows that quantum computers can be actually useful, at least in medical field. And our third example comes from Japan and from Research Institute Riken. So what they did, they connected IBM's Quantum 2 system together with Fugaku. And Fugaku is one of the most powerful and large supercomputers in the world. And this is a great achievement because they used a closed loop workflow to simulate iron sulfur clusters. So how it worked, we used Fugaku supercomputer, all of its nodes. I think it was 158,000 nodes. So you can imagine that the whole population of Klaipėda connected to quantum computer and worked together with it. And this experiment, what it showed is that our quantum is not really quantum versus classical computers, but we are striving for architectures that takes the best of both worlds, of quantum and classical computers. Okay, so this is a lot of fun that others did, but can we do something by ourselves? So IBM has OpenPlan, and what OpenPlan provides you is 10 computing minutes per month, absolutely for free. I mean, you don't need to enter your credit card, you don't need to pay anything at all. And this subscription, at least for now, it renews every year, every single one. So you might say, oh, okay, so 10 minutes, it's not a long time, but as we know in practice, at small or when you're learning, you only use a few seconds of computing time per one run. So actually, it's a lot of time. And if you put it into perspective, one computing minute costs around $96. So, you know, IBM is giving you $1,000 per month absolutely for free. So be clever, connect to it, use it, and create something fun. Okay, so this is all from my side. As I mentioned, tomorrow we'll have a quantum workshop from Artem and Manta. So if you want to start your journey, this is the place where you can do it. Okay, so thank you everyone, and hopefully see you tomorrow.